Hello and welcome back to our series on multiple regression analysis. So in our last video, we kind of just gave a high level overview of what a multiple regression analysis is. We discussed kind of the example that we're going to be covering in this video, and then we loaded the data into a data frame in pandas and then some basic transformations. So in the following couple videos, we're going to actually start exploring the model. We're going to start talking about different things related to the model. But before we actually get to that point, I think it's very important to understand some of the assumptions of the model. So when we do a multiple regression analysis, there are certain assumptions that have to be met in order for us to say that our model is working the way we are expecting it. And so some of those assumptions I've listed down below for you, and I might not go into too much detail at this point because I think it's nice to have a visual or an example to kind of build off of. But the first assumption of our model is that the regression residuals, so the errors, must be normally distributed. And so this is the first assumption. Basically, what it's saying is that there shouldn't be kind of any weird distributions with our errors. They should be relatively normally distributed. It might not be exact, but the general idea is that they should be mostly normally distributed. We are assuming there is a linear relationship between the dependent variable and the independent variables. This kind of is self-explanatory because if it's not linear, you probably shouldn't be using a linear regression analysis. So you shouldn't be trying to model non-linear phenomenons using a linear model. The residuals are homoscedastic and approximately rectangular shaped. Basically, what this is saying is that the error terms are constant. And so, again, this will make more sense when we cover the topic, but basically, what you don't want to see is that your error terms are either shrinking or growing over a specified period of time. They really should be staying constant regardless of what point in time you are. There is an absence of multicollinearity. So that means there is no multicollinearity. There should not be any. The reason why is that that's basically saying that there are multiple variables that are basically saying the same exact thing. So it's redundant, and there's some side effects that we can see in our model if we have multicollinearity. Finally, there is no autocorrelation of the residuals. In other words, there is no kind of underlying pattern in the residuals. They should be random. They shouldn't have any pattern that I can follow. And so what we're saying is that there is no autocorrelation, so that you can't kind of look over time and seeing this particular pattern of in the residuals. So there should be no autocorrelation. And again, we will discuss that in more detail when we reach that point in the model. Okay, so just to recap, we did load the data into pandas. The first thing that we're going to do now is we're going to check for multicollinearity. And so what I did put down here is I gave a brief overview about what is multicollinearity, what is the problem with it, and how do we test for it. And so to give you an idea of basically what it is, I like to kind of use an analogy, and I found this analogy online and I thought it was perfect. Basically, imagine you were at a concert or something like that, and there were multiple people on a stage, and all of them were singing. And I asked you a simple question: who do you think sung the best? So who was giving the best performance? Well, it's very easy to answer that question if you can distinguish each one of the band members from one another. However, if they all begin to sound the same, and then maybe they're all singing the same notes and things along that nature, it might be very hard to distinguish one band member from the other band member and when they're singing. And so that's kind of the idea with multicollinearity is the variables are behaving so similarly, it's kind of hard to answer the final question, which is what is the impact that each variable is having on the model? The reality is they're kind of having the same impact. So you can't really say for sure whether this one is having this impact because they look and behave almost identically. And so that's the hard part is it becomes very difficult to distinguish two variable effects on the model since they behave so similarly. There's also kind of a performance aspect, which is why are you adding in information that's not actually giving you any additional value? Why are you adding a variable that isn't actually telling you anything more about that model? You already have one variable that's telling you all the information. So why are you adding another variable that's basically telling you the same thing? It doesn't kind of make sense. So that's another reason why we would want to kind of get rid of perfect multicollinearity. Now, there's also kind of a problem when it comes to our estimates that are produced. And so the first thing that we'll talk about is the problem with multicollinearity is that the coefficient estimates, so the coefficients that we basically predict for each one of our variables, they tend to be unreliable. Additionally, the standard errors of the slope coefficients become artificially inflated. This leads to a greater probability that we will incorrectly conclude that a variable is not statistically significant. So there's all these mechanics that are going to be going on behind the scenes that can happen if we have multicollinearity. So now that we understand the problem with multicollinearity, how should we test for it? Well, lucky for us, there actually is a couple tests that we can do. I'm going to talk about a particular one a little bit later down the road. But at this point, what we should first do is just kind of check and visually tell, do any of our variables have what we might expect for when it comes to multicollinearity? And so basically all we're trying to see is how correlated is one variable with the rest of the variables. So easy way to do this is we're just going to do a correlation matrix of our data frame. So print out a correlation matrix of our data frame. And we'll create a new variable. We'll call it correlation econ df, and then we'll call the correlation method. And then from here, we will display it. And so we'll say display correlation. And then what we'll do here, oh, sorry, I don't need those brackets. And so then we get this little thing back. With correlation matrix, it's kind of hard to tell because a lot of times there can be a bunch of information here. But basically what we're looking for is, I think a good example was like right here. Perfect. So birth rate and population growth. There's a correlation of 0.97. That is extremely high. They are almost moving identically. It's almost like we have two lines on top of each other. So this would be a perfect candidate for multicollinearity because that correlation is phenomenally high, and that's not a good thing. Basically, what I'm saying is population growth and birth rate are basically the same thing. In fact, that makes sense. Because if your population's growing, it's probably a result of either A, less people are dying, or you have a higher birth rate. So that makes sense. Now, I put these variables in here on purpose because I wanted to demonstrate this. There's actually a couple in here that you will see are very highly correlated. And so when we do this, again, with a correlation matrix, it's a little bit hard to tell. What I like to do is I like to put it in a heat map because I think a heat map just kind of helps you visualize very clearly like where the pockets of multicollinearity could be existing. So what we'll do is we'll plot a heat map. Plot a heat map. And so what we'll do is we'll call SNS, which is, again, our Seaborn library right up here. And inside this wonderful library, there is something called a heat map. It's wonderful. We'll pass through our correlation matrix, and then we're going to set some labels. So we'll set the X-tick labels equal to the correlation columns, so just the column values. The Y-tick labels, again, I want those just to equal the correlation columns, and you'll kind of see why in a second. And then I need to choose a coloring scheme. The default one, I really don't like it. It's kind of hard to distinguish one from the other. So what I like to do is just two very high contrasting colors. So I do red and blue, just like that. So red, blue. And then from here, what happened? Oh, did I misspell something? X-tick labels, ELS. Oh, that's why, because I misspelled it. Perfect. Okay, and then so you get this wonderful heat map, and really what you're looking for is something that's either very dark, so very dark blue, or very dark red. Now, along the diagonal, these are going to be ones because you're saying, well, what's the correlation between GDP growth and GDP growth? Well, they're the same thing, so they should be 1. So going down the diagonal, everything should be pretty much dark blue. In fact, it should be dark blue. Now, what I'm looking for is things like right here. See that right here? That birth rate and the population growth? that's very high. So again, that's almost perfectly dark blue. So this would be a candidate to potentially remove. Even down here, that's kind of getting a little bit high as well. Um, Household consumer growth, final consumption growth. Basically, what this is telling us is it's almost identical. They're the same thing. And so how can we do this in a systematic way? Because ideally, okay, yeah, visually we can tell, and sometimes that's fine. Sometimes it's fine just to visually look at it and kind of say, well, which one should I remove? Well, we could do that, or we could actually use a metric behind the scenes. And so there's actually a metric called variance inflation factors. And so what this will allow us to do is it will allow us to do a quick measure of how much a variable is contributing to the standard error in the regression. Really, what we're going to find out is it's a really great way to help measure the amount of collinearity in a set of multiple regression variables. And so this is kind of a system or a method that we can use to help detect multicollinearity in our data sets. And it's doing that by basically seeing how much a variable is contributing to the standard error in the regression. And so when significant multicollinearity issues exist, the variance inflation factor, so the VIF, will be large. So if it's large, it's basically saying, hey, there's probably multicollinearity. And so how do we build this whole system? Well, lucky for us, there's already a library out there that calculates it for us, right? That's the wonderful thing about it. Okay, but I'm going to kind of jump ahead a little bit, and what I'm going to do is I'm going to say the econ df before equals the econ df. We'll explain kind of why I'm doing this later, but this is just so that way you guys can compare the two after we've done the calculations. So right here, I'm just going to redefine my data frame. Unfortunately, what we do have to do is we have to add a constant when we pass it through this particular function. And so what we're going to do is we're going to take our stats model library. We're going to call the tools, and then we're going to say add constant. And then that will equal the econ df before. And then from here, what we're going to do is we're going to create a series for both. So create a series for both. This is basically where we're calculating the variance inflation factor. And so we're going to create a series underscore before, which equals a panda series. And then what we're going to do is we're going to call our brackets and then our square brackets. And then it's going to be variance. Oh, I thought if I did that. Oh, there it goes. Variance inflation factor. I'm going to pass through my x1 values. And then we're going to say I. And then we're going to say for I in range. And then we're going to say x1 shape 1. And then that's good. And then we're going to say index equals x1 dot columns. Looks a little bit complicated, but I promise you it's not that much. All we're doing here is we're just using list comprehension to create a list. And all we're doing is we're basically looping through each value, and we're going to calculate the variance inflation factor. And then from here, we're converting that list into a series, and we're going to give it an index, which is just the old column name. So hopefully that makes sense. If you take a look at it, I promise it's not too bad. At least I tried to say. So what we're going to do now is we're going to display the series. And so just a note to ourselves, because we're going to see we're going to do this twice. We're going to say data before, and then we're going to say print a new line. And I just like to have 100 of these little guys. And then we're going to say display series before. Perfect. And for I, my bad. I forgot to put that in there. Okay. So the general rule, and this is just a general rule, if it's above 5, you drop it. Well, if you can tell here, GDP growth, we don't really care at this point. That one we want to be highly correlated. But for example, population growth, birth rate, we're saying there's multicollinearity there. Final consumption growth, government final consumption growth, household consumption growth. So some of these should be dropped. And so let's drop some of them. So what we're going to do is we're going to create a new econ data frame, and we'll call this one after. And then this will equal the econ df. And then we're going to say, and then we're going to call the drop method. And then we're going to drop some stuff. So we're going to drop GDP growth. And then what we're going to do is we're going to drop the birth rate. And then what we're going to do, we're going to drop final consumption growth. I think that's the one, yeah. And then gross capital formation. And then we have to specify an axes. And the axes is equal to 1. So we want to drop those columns. So we're going to drop GDP growth, birth rate, final consumption growth, and then gross capital formation. And then what I'm going to do here is I'm basically just going to redo all the work I just did, which is just change this one to x2. And then we're going to call this one econ df after. And we're going to copy this little guy right here. And then we're going to call this one series after. Series after. Instead of x1, it's going to be x2. And then I'm just going to copy this little guy right here. We'll call it data after. After, and then series after. Okay. What happened? Oh, that's why. I forgot to change that one. So data before, data after. Don't worry about the constant because we're not keeping it. But now we can see everything's within the threshold. So now everything is below 5. So if it's above 5, you probably should drop it. And then once you drop one of them, magically what happens to the other one? Well, now it's not going to be, there's nothing where it's going to be highly correlated with it. So because we dropped birth rate, it dropped population growth, which makes sense because they were basically saying those two were pretty much one and the same. Gross capital formation, where is it? Or gross capital formation growth. That was fine before, so that's not the right one. Government final consumption growth, that was 35. Now it is 1, so that's good. Household consumption growth, that was like way high. Now it's only 2.7. Unemployment was fine. So overall, we're kind of good. So we've taken care of the multicollinearity component of it, which is good because now it makes sense because we detected the ones visually by looking at this, and then we approached it with a systematic method at play. So we used the variance inflation factor to remove the columns that we believed to be having multicollinearity. And once we've done that, we then validated our work to say, hey, okay, everything seems to be working fine now. And again, this is just to kind of add on to it. You could also visualize it another way if you wanted to. So you could define a scattering plot that I think does a really good job of also kind of help just looking at. So if I call pandas plotting, and then we'll do scatter matrix, and then I do econ df after, and then I want some transparency. So I'm going to set, well, actually, I don't want any transparency. So I'm going to set alpha equal to 1. And then I'm going to do a fig size of, I think I had it 30 to 20, something like that, 30 by 20. And then I'm just going to show that plot. And then we're going to say show the plot. And so we'll do plot dot show. And then we get this wonderful scatter matrix. And so down along, it kind of is just showing you like a little bit of the distribution. And then you're seeing the scatter matrix or the correlation matrix between each one. So you're saying, hey, here's broad money growth with population growth. Here's, things like that, and, everything that we want. And actually what I'm going to do is I'm going to keep that one like that. So actually I'm just going to keep the econ one. Because this one technically it's okay if we want them kind of more correlated. And here, if I run this again, there we go. So with GDP growth, you want them kind of going up like that. So you want kind of these more linear relationships. With everything else, you want like these scattered plots. So things that are kind of just look more random. There doesn't seem to be any kind of pattern behind it, because basically what that's saying is that they're not correlated with each other. So that's ideally what we want, is we want kind of these more scattered situations like that. But then with our explanatory variable, we want these kind of nice upward trends and things like that, because that's saying there's potentially a linear relation there. So that's kind of the important part about that aspect. So with that being said, I am going to finish the video for this particular topic. If you have any questions about multicollinearity, or kind of just the steps that we went through in this video, please put them down in the comments below and I will try to get back to you. Again, all we're doing is we took our data set, we created a correlation matrix. We then did a heat map to kind of help us identify which ones we thought were going to be candidates for dropping. And then we used a systematic approach to basically say, hey, these are the ones that crossed a certain threshold using the variance inflation factor, which allowed us to then determine which ones to drop. And then I kind of just gave you a little bit of an extra topping, which was, hey, there's another way we can visualize this, and we can use a scatter matrix to do that as well. And then ideally here, what we want to see is kind of random for all this stuff, but then along the GDP growth one, I know it's kind of hard to see, but unfortunately there's just so many variables. But if you take the Jupyter notebook, it'll be smaller. You kind of want these more upward trends. So thanks again for watching, everybody. In our next video, we're going to talk about outliers and whether we should remove them or not. So see you in the next video.